Recording in progress.
That's exactly what I was gonna ask. We'll need to push the pound button on the console. Sorry, I had the. Wait, so it's in your touch tone. There you go.
Great. Good morning, everybody. Thank you so much for being here. It's a pleasure to have Tomasz Malkiewicz here with us. He's the interim director of a Nordic infrastructure collaboration for the year 2025, and he has managerial and specialist positions at the IT Center for Science in Finland, and he's worked there since 2011. He holds a PhD in nuclear physics from the University of, that I cannot pronounce, Jyväskylä in Finland. So welcome to ISI.
Thank you very much, Eva. Thank you for having me here. Eva booked roughly 1 hour for us. I'm also willing to take questions as they come. So we have here some stuff that perhaps could monitor and let me know if there are some questions. So please don't hesitate to interrupt anytime. And also after the talk, I'm happy to take also more detailed questions. Where I'm coming from, it's multiple positions in Finland and in France. I'm originally from Warsaw University of Technology. And now in this position at IT Center for Science, I've been for the past 14 years. In the Nordic collaboration, I've been for 8 years, and the majority of my talk will be dealing with the position at IT Center for Science, CSC, in Espoo, Finland. Eva indeed suggested that we approach it from the European perspective and Nordic perspective, and that's from where I'm starting. So the Nordic perspective here, the Nordic collaboration is basically collaboration of 5 Nordic countries that you see there, and Estonia, that is also very advanced with IT. And these countries work together based on the funding from the Council of Ministers and other sources, national providers primarily, to provide infrastructure solutions that are competitive, not only Europe-wide, but worldwide. How it works, we do have several projects that are running more or less independently, and one of them is directly supporting LUMI. That is the main topic of my talk. Then we have the lightweight coordination for this loosely related projects. In total, we have run roughly 30 projects in this Nordic collaboration. And here is the funding scheme. So some of the funding comes from the national providers and some is coming from communities, for example, sensitive data community or high energy physics community. So that's how one gets funding for these. And then we have a certain methodology, like a factory, when the new community enters the system and would like to have a successful project, then we have all the methodology in place. You can call it collaboration as a space. For the Nordics primarily, but we do have collaboration also outside Nordics. And the long-term approach is the key here. But the main bulk of my talk today will be related to LUMI, one of the fastest supercomputers in Europe, currently on the 3rd spot in Europe. It used to be #1 for a long time. 1.5 years, that is quite long scale in this field. And the Nordic collaboration contribution to that is the project called Puhuri that provides authorization and authentication for all the users to approach LUMI. So that's this Nordic perspective here. And then let's then go a little bit deeper into the LUMI machine. So it's a unique consortium. Currently 11 European countries coming together, getting funding from the national sources, ministries. And this funding is matched by the Euro HPC funding coming from European Union. In Europe, there has been consistent emphasis on HPC over the past years, and this trend tends to continue. We have Ursula von der Leyen talking that indeed AI is the path forward, and indeed also funding is following this way of thinking. The total budget of LUMI is 202 million euros, and this is half funded by European Commission, so the Euro HPC, and half funded by this 11 countries. And then also the quotas on the machine follow this trend. So half of the machine is under the jurisdiction of Euro HPC. They have their processes for allocations on the half of the machine. And then the other half is divided by these 11 countries proportionally to the amount of funding that they bring in. Finland brings currently the most of the funding. It's roughly 22% of the whole machine is then under the Finnish jurisdiction. And then there are local allocation committees that decide case by case for these countries. In general, LUMI, up to 20% of its capacity can be used by commercial applications, by business, and so on. There are various paths, and this depends case by case how it is allocated, but up to 20% is available for the commercial use. And what to be mentioned is that LUMI is in the first place dedicated to research. So no classified, I mean, to the standard research, if you will. So no classified research on LUMI. Then these are these European countries forming the current LUMI consortium. And here is what one gets out of it. So that made it basically roughly 2 years ago. It entered top 3 on top 500 list, and also very high on the green top 500 list. And it stayed at this very high position for roughly 1.5 years as the fastest machine in Europe through this capacity. And this is through the GPUs, through the AI applications, and I will have some, so to say, hands-on also, if you will, examples how this capacity is in practice used. Then in Finland, in general, there is an approach that even with such top of the top machine, you would like to serve the wide variety of users. So it's not a dedicated machine to, for example, one field of science, but one would like to, so to say, serve every community that had this high computational demand. Therefore, here you see the architecture of the machine. You have the LUMI C partition, that's the CPU one, with AMD Milan CPUs. I will go a little bit deeper into that, how it exactly looks like. Then there is a container cloud service available, object storage of 30 petabytes available for the users. Then the quantum computing. I'll have one more slide, so I don't go there into the quantum now. Then what makes this computer one of the fastest in the world is this LUMI G, so GPU partition, consisting of AMD MI250X GPUs. Then there is an interactive partition for data analytics of 32 terabytes of memory. Then the flash storage of 10 petabytes, and the Lustre storage of 80 petabytes. With this setup, one is really able to serve a vast group of users. I wouldn't go that much into the details, but how it is, the big picture here, how the resources are divided in Finland. You have at the university local clusters, and their size vary university by university. And then you have the IT Center for Science, CSC, from where I'm coming from, and that is the, so to say, national provider for Finland. It means that all the big machines are procured and operated by CSC. This is quite unique solution, both on the Nordic scale and also worldwide. Similar center, also of the similar size, is in South Korea. It's called KISTI. So KISTI has roughly 800 employees and also is running procurements and supporting with HPC resources the entire country. That's the primary source there in South Korea. Similarly here, CSC currently has around 700 specialists. Out of these, roughly 80 to 100 are directly related to LUMI operations and supporting the users of LUMI. In Europe, similar thing is with the former SARA center in the Netherlands. Otherwise, in general, mostly in Europe, it's like this, that, for example, in Sweden, you have universities, each of them owning some resource. One university could be good with GPUs and serve the broader user base in Sweden for the GPU needs. Another university maybe focus on CPUs, and they collaborate and so on. So here, it's one to serve them all. This is this one slide that I've mentioned regarding the quantum resources. Through LUMI, we've been prototyping already last year with access to some limited quantum resources in Sweden and in Finland. Now, recently in Finland, there has been 50 qubit machine, 50 qubit 50 inaugurated. It's a little bit complex, the access scheme, so it's not straightforward for everyone to, so to say, get access to it. But our view in Europe is that we would like to train the users already now into quantum. This has been a long-term effort. Myself, I started like 2012 learning the D-Wave annealer, for example, and base stuff. And we think that through whatever now is coming, although one cannot do real science with it, but by getting the heads dirty, by trying something hello world type of words, we will train the user base if and when something significant comes on quantum. So that is also the paradigm that will carry us on through this presentation, because now I'm talking about the LUMI that's currently in operation, but I will have some slides on the successor of LUMI called LUMI AI Factory that has been also in the title of this talk. There, the quantum part is also a significant part. So as you hear from my presentation, indeed, Europe is investing a lot into AI, number one, quantum, number two, currently. Yes, so I have something for you to have a look. It's how the data center where LUMI is located looks like. This is located 600 kilometers north of Helsinki in the remote location. Roughly since 2015, the Finnish supercomputing resources have been moved from Helsinki up north for cost efficiency. That's how the data center looks like. That's the former paper mill. It's no longer in use. and accommodated to host data centers. Maybe it has been also a issue here that also hyperscalers put the data centers in the Nordics and in Finland. So that's actually close to the data centers that is now being built for one of the hyperscalers. These are the LUMI racks. This is the HPE array machine. You see the beautiful area of Kajani, and indeed this paper mill fast capacity that provides both very good power as well as is very well connected in terms of fibers, fiber links. A little bit about this excess heat utilization. So roughly 30% of the excess heat coming from LUMI is used for heating the Kajani city. It's a city of around 70,000 inhabitants, and indeed they get heat at home from the excess heat of LUMI. The temperatures may go up to -25 degrees. When I was living in Finland, in Helsinki, we did have something like -2 degrees. There in Kajani, there was still around -10, that amount. So basically, for a large period of the year, there is a need for reusage of this excess heat. And a little bit, some overview of the specs of the data center itself, hosting LUMI. And I mentioned this high-speed fiber connections. So we are talking about 200 gigs, 400 gigs, and then outwards, for example, to Germany, 100 gigs, and this being upgraded. And these lines are also redundant. So one connection goes from the south, another to the north. So even if there are some outages, the connection stays intact. Okay, so some stats. This I prepared for supercomputing in Atlanta. Number of users, over 5,000, and active, roughly 2,400. What it means active, that has logged in and did something on the system over the past 12 months. And you see the stats there, how much they consumed by the time in terms of CPU and GPU hours, and sorry, the quantum seconds I should convert to hours, so sorry. I'll do that for the next one. But as you see, in general, the utilization of the order of 80–90%, that is optimal for this kind of devices. Some longer breaks, some of them were failures, and some of them are also the maintenance breaks. So usually one can, to some extent, combine those. But in general, LUMI has been well in operation for a longer period of time. And this has been the first of the European so-called pre-exascale machines. Now there are 3 such pre-exascale machines in production. Another one is Mare Nostrum 5 in Barcelona, Spain, and the third one is Leonardo in Italy, Bologna. So that was basically the European view, that we invest into these pre-exascale machines, and now we'll go forward to the exascale. In terms of users, that was yesterday. I've been to San Diego, also thanks to Eva for arranging that, and then discussed with Frank and Christina and others. So they were very curious about switching users from NVIDIA GPUs, where they have run for many years, to AMD. And they are ahead of the same operation for the sake of Frontier, that is also with AMD. So they are also in the process or starting the process of the switch of the users. So what it takes? Well, it's case by case. For example, the standard code that can be given as an example is ICON. This is for climate research. And then it roughly took 3 to 5 full-time equivalents, 3 to 5 FTEs for getting the code switched from NVIDIA to AMD. So it's really a major effort. And rule of thumb that I used to give, that let's say that, well, 50% cases would be easy. So you just do so-called heapify your code to get it from CUDA to ROCm. You run heap on your NVIDIA code, CUDA code, and you get something that works well on AMD. But then the remaining, let's say 35 to 40, will require major effort, like this ICON. And unfortunately, some of the cases are so cumbersome that it's not worth the effort to translate. So for this example that I gave, also when doing this translation, a lot of bugs have been found. So that has been a positive thing, because it was an very old code that had a lot of, so to say, small bugs here and there that got fixed in the process.
So Tomasz, can
Yes.
AI help you with the translation between the various codes? Or?
Well, these are usually complex. Fortran, whatever, 77. Then you have all kinds of other flavors, newer libraries. It still requires human in the first place. And the colleagues with whom I've discussed, so when they actually ask AI for help with that, so most of them tell me that they, so to say, wasted more time into dealing with AI than if they would, so to say, go straight.
Mm-hmm.
I promise you to go really deeper into the architecture. So on the left-hand side, you see the GPU architecture. I'll have also better view on that, but you can see that there is roughly 3,000 nodes that make this amazing performance of LUMI. And on the CPU side, as I mentioned, the AMD Milan processors, and roughly 2,000 nodes with 256 gigs. And this slingshot interconnect extremely fast, basically Ethernet-like connection inside. Okay, and here I promised this deeper view. Here you see the view of this nodes, how the node looks like, how many so-called GCDs, so graphic computing dice you have per node, and then you have the total number of GCDs there. So to give you a flavor, you saw that there were indeed some longer breaks, and when restarting LUMI is given to our specialist to actually test it. So with this ICON code that I've mentioned, it has been tested on 2,800 nodes, so basically the whole machine, and it has run successfully. Some of the training machine learning codes, they have been tested with so to say various success rate for really trying to take all the machine. But this amazing amount of graphic compute dice, and then inside of this, of course, how GPU works, you have let's say 110 threads in every of these. So this makes this huge amount of computation that you can perform with that. So that's why you can run this big climate models and so on. You split the single jobs into the single computations, excuse me, into these threads. So then they run the whatever algorithms you give them, and from time to time you check the results. You do the domain decomposition, if you will, again, and run and so on. And this brings this amazing power. Okay. So here the architecture, so all-to-all connections, and as I mentioned, super fast connections between all basically the nodes that are grouped, six groups you see there. Very good solution. All right, and now I promised you to get your hands dirty a little bit. So I've, with the help of my colleague, Lucas, he was actually testing PyTorch. How many of you have heard about PyTorch? Okay, almost everyone. Yeah. So that was our testing case, running some machine learning stuff on LUMI. So that's the terminal. Once you log into LUMI, that's how it looks. So LUMI means in Finnish snow, but as you saw from my first slide, the symbol is a wolf, and it's not a Finnish wolf, it's Canadian wolf on this picture, but as you see, it propagates also to the login node. Yes, and then you have various queues, standard GPU queue, so LUMI G on top and LUMI C for the CPU, and then for benchmarking some other queues. That's what is available, and we go with Slurm. We've been going for very many years with Slurm, and are happy with that. So some more details about various queues like large memory and so on available. And then for the storage, so I gave you some numbers, how much flash there is, how much ceph there is, and here you have some more specifications of that. And yeah, we do run some cleaning scripts. I discussed in San Diego that there it's more custom made, that they so to say contact the users and check with them, could you please please move your data and so on. Here we've been actually forced to semi-automatize it. Okay, and then just to say that there is all-to-all basically for all the storage elements. And then, well, how one operates on LUMI. So I've been with HPC roughly since 2004, and not much has changed. So as Eva said, I'm originally nuclear and particle physicist by education. I did my PhD on ALICE experiment at CERN. So I was basically already in 2005 using the similar kind of comments for running at the super machines in Finland at the time of my PhD. Okay. So batch job screen script, how it looks like. You basically define the parameters, and then with srun you are good to go. And this is on the single, this GCD, graphic computer die, and I will have now the example of running on something bigger, and you have the documentation. I think I could share the slide later to Eva if needed. You will be able to look up. So that's sorry how one runs on the single GCD. So simply submitting the job with sbatch command once you have the script. And then let's something about monitoring. So also nothing special there. Canceling the job standard way with Slurm. Then single node. So then you define how many GPUs per node. So it's 8 in this case, and some other parameters for your batch script, and then srun as usual to run it. Okay, and then let's go a little bit further. Some performance boosting, CPU bindings here, but what is more interesting, training on multiple nodes. So here with 2 nodes, you just define it in your script, and there you go. So I don't have more on that than that, but yeah, I think you get a flavor. So if I may ask, does it ring a bell? Would you use your machine in a similar way? Yeah, I see people nodding. So
What's up with the memory equals 0?
let's see.
Like I said, you never. No. It was a multiple one. If on that one, right?
Yes.
You're saying I want all these tasks, but I don't want any memory.
I think
That's a good question. Let's see in the previous jobs how much
It was memory equals 0 as well.
here.
Yeah, it probably means everything or something, but yeah.
Exactly. Yeah, that's a good spot. I should look it up. Be able to comment.
You're a good debugger.
Yes. Thanks for the eagle eye. Good. Then let's go to AI and science cases, since that was the request of Eva to impede you a little bit what kind of science cases we have on LUMI. So around 50% is going into training the models, machine learning. And this is indeed as nuclear physics or particle physics 20 years ago. As much as you give, as much will be eaten, so to say. That really holds for all this machine learning codes. And then this traditional simulations, so using CPU and GPU, I will have also some more details on that. So this is, for example, this icon, the climate model that I've mentioned, that can give you up to 5 kilometers now accuracy, or even below for the simulations. Okay. Then, so already now with this architecture is what we have. It's very well suited for the AI, and that's the trend also that will carry us to the next generation, that there will be even more emphasis. But as I said, we still want to keep this HPC part because of the use cases that we have. So we are not interested in having purely GPU-based machines. And interactivity. So we have the graphical user interface based on Jupyter notebooks for running the interactive jobs, but most of the users actually, in our case, are happy with this command line scripting. No issue there. Good. Then I will have some concrete examples of this science AI.
So just a question. So, you said that users are happy with the command line.
Yes.
Is it because you do a lot of training on command line, or is it because people already come in and they're familiar with, command line interfaces? And
that's a good question. So the answer is that in Finland, even since I started there in 2002, I came to Finland. Already there was a long tradition of having these central national resources. So the groups are there. So you may get a new graduate students that enter the groups, but you have always some senior persons that are acquainted with how it works. So as I mentioned, not much has changed. You still have SLAM. And in terms of training, yes. So CSC provides a lot of training, and then we have through the Nordic collaboration a lot of training. So usually what professors or PIs do, send their newly recruited students immediately to the courses. So the courses would be introduction to MPI programming, and then one either chooses the C++ path or Fortran path. So both these are available, and of course all these Python things that are also around.
And in terms of you showed some of the workload information, but in terms of like MPI job versus sequential jobs, do you see, simple jobs that people run? Do you see a difference? Is it mostly MPI jobs that are running on the system? Or?
Definitely, because that's also a good point. So I started talking about this, that at the universities in Finland, you will have the smaller clusters. So the smaller users can use the local university clusters. And then there are two supercomputers in Finland, independent of LUMI. One is called Puhti and another Mahti. So Mahti is also quite powerful machine. Puhti is for this more longer term jobs, single jobs. So here actually, when you apply, we may ask for some scalability test and so on. So here we really get the users that know what they are doing.
Yeah, in the US, it's a little bit different. The supercomputing centers are running all sorts of workloads, including single core.
Interesting. Good. So these are my science showcases. So for the language programming, that's a good example. This Silo AI, Finnish company that now was sold to some big other big company recently after developing and training the models on LUMI. So that was the early cases. We gave the resources, trained, and now this is really return of investments, if you will, or benefit realization. You get all the startups, they grow and they become recognizable even worldwide, and then of course you get some, also the nationally you get through the taxes some return. Okay, then some other case from Czech Republic, also similar training. For the sake of time, I will move on. Physics, materials, quantum mechanical calculations of inorganic crystals with significant speed up. So these are some showcases for science here, and yeah. So as I said, Europe is investing into that, and we see the growth and we support the growth. So what I did not mention is that we have 3 levels of support for the users, and level 1 is basic support, level 2 is more difficult problems, and level 3 the most difficult case is porting and really optimize. So we get a scientist with their case, we can provide really significant support, and it's included, so to say, in the package, unless it takes really significant amount of time for this level 3 guys to support. Yeah, the bio digital twin and climate digital twin, so allowing simulations at unprecedented scale. Here you see the workflow. Yeah. This is with our package. So yeah, this bio applications are also often with this kind of things, and TensorFlow here. Then for the climate, this will be maybe my best showcase here. So as I mentioned, this global climate simulations at the unprecedented resolution of 5 to 10 kilometers over multiple decades. That's what it is. And here you have the workflow. You have the user that submits the job. There is a workflow manager, and then the blue box is LUMI, basically using GPUs of LUMI. For this part of codes, these engines that benefit the most of the GPUs. And then the red box is Mare Nostrum 5 in Barcelona. In this case, these are the CPU jobs. So you can really nicely, with your workflow manager, separate your job and really get what is needed to be calculated over GPUs, CPUs, and then merge the results. And here, yes, a little bit more about the workflow. 2 models, for example, and how they are then processed.
Can you talk a little bit about the data lake, the data bridge and data lake, what's happening there?
I'm not an expert, so
okay.
Yeah, we can look it up together. after the talk on that. Good. Yeah, and that's something that I'm interested actually myself quite a bit. So maybe here in California it's not a hot topic, but it is for us in the Nordics. Glacier calving simulations. Greenland, when I was flying here, first time actually the flight takes over the Greenland. You fly, and it's quite quick, 11 hours from Helsinki to LA. So very, very up-to-date topic. Sea ice break, also connected. On the left-hand side, you see the satellite view, and on the right-hand side, you see the simulation view. The code is called HIDEM. This is this domain decomposition that I've mentioned using the single threads. So that's the standard calculation that each of the threads can perform. So you are able to decompose the whole area into smaller domains and use it the most efficiently with very accurate scale. These are for the real applications. You see how the ice will be breaking. This is needed for example, ships that are moving over there. Also in Greenland, it will be for the people living there to know what kind of paths that they can take. This simulation can run for whatever, 18 hours or something, and you can get really accuracy of unprecedented scales because of these huge resources available. And here I have for you the simulation. So this will be the power generators in red, and this is the ice that is now, as you see, breaking. So thanks to that, you can get all the forces that are applied to, for example, the things on ice there. When ice is breaking, one can really calculate how it will impact the objects there.
And by wind power, do you mean like wind turbines?
Yes,
Okay.
precisely. These are the wind turbines. Okay. Let's see. One. And now for the last 10 minutes, I will bring you to the future. That's something that has been recently announced, unprecedented investment, not only in the Finnish scale, but also Europe-wide scale. So the successor of LUMI, it's called LUMI AI Factories. Funding of over 600 million euros, roughly 1/3 coming from EuroHPC, European Commission, and this is matched by the national funding. That's what is coming, fresh, so to say. The vision, empowering Europe's AI ecosystem, AI-focused computer, but again, we aim to have this capability of running also the HPC jobs, as currently we have, and also quantum computing and AI workloads in the future as well. And the infrastructure is ready because the LUMI warehouse is really big and can accommodate also this unprecedented resources that are coming there. Right. That's the vision. So combining, as I mentioned, AI, HPC, and quantum computing. Here you have the consortium. That there was a very aggressive timescale for getting the bid in and so on. So that's the countries that were able to commit in the given time frame. Yeah, and you have the total budget spelled out there. So factor of 3 higher than the current LUMI. So in Finland, people are usually modest. So we say that we are aiming at top 3 on top 500 list with this amount of available funding. Okay, and that's the timeline. So we have the current LUMI system that I've walked you through, operating until 2028, and also there are some plans that to maybe continue operating it also after the end date. And then you see very nice overlap with this new system. So the project will be launched in 1 week, right? A little bit more, 2 weeks from now, and huge investment also. CST is recruiting. If you are interested in filling the Nordics, so welcome to the webpage and also check out the opportunity there. Really many open positions. So yeah. Yes. And now, what will be the key industrial sectors and focus areas? Well, the big companies in Europe, they are interested. Also, the consortium is active, looking for such cases, and there are often the national mechanisms. For example, in Finland, it's Business Finland, through which one can, so to say, apply for grants for using the machines like LUMI. So that's this company side, and then the new thing is sensitive data. At the moment on LUMI, there are not that many sensitive data cases. Also, it's because of the architecture. So you cannot really properly separate the users, get the necessary clearance and whatnot. So the goal is to have it somewhat in better shape for the AI factory. The work has started now, how to have the design of the system, these spaces, so that one would be able to separate out of it for the sensitive data research. And then this communication technologies and networks as a next pillar. Okay. I don't know how popular it is in US, but this trustworthy AI, regulatory compliances and consultations and so on, that's something also in the Nordics that is a hot topic. So also part of the LUMI AI factory will be this reliable and trustworthy and ethical usage of AI. So these are not really buzzwords. There are some concrete plans how to work on that. Data is also another kind of focus area. Yeah, so building the whole ecosystem of the data as a service, included. Basically, one would like to serve all the user base with the data solution needs that they have. Good. So I'm almost done. What can be said about the architecture? Not much, because the tender will go out after summer. So, well, let's say as much as can be said at this stage. That's the current vision. So again, the main part being the GPU partition, then the CPU multi-core partition, and then the quantum part. So some percentage of this 612 million euros is indeed into the quantum allocated, and there will be a project starting on that as well very soon. Yes, nothing special here. Flash-based and Scratch storage, disk space, and then the object storage LUMI. Yes, and again, similar backdrops stuff that I went through with you earlier. That's the current vision of the system. Architecture vision. You see maybe some familiar terms there. Easy build, Conda. Then Jupyter Hub, MLflow. Good. And then the overarching goal. So world leading quantum accelerated AI infrastructure to all of Europe, because it's Euro HPC funded, so we are somewhat restricted to Europe here. In line with European Commission, as I mentioned. Good, so I'm ready.
Thank you very much, Tomasz. If people online have questions, also people here